Hello, and a very warm welcome to the second day of the Cybathlon Symposium 2020, again live from Zurich. My name is Olivier Lambercy, and I'm delighted to be your host for this event, together with my colleague Roger Gassert, who you will join us in a minute. I hope that you were able to join us yesterday, as we had a fantastic opening of the symposium, with a great set of speakers and fascinating talks covering the topics of powered wheelchairs, functional electrical stimulation, and exoskeletons. If you missed it, don't worry, you can still find the stream of the entire day on our landing page. But please stay with us now, because we also have an exceptional program ahead of us today, this time with a focus on brain-computer interface, arm prosthesis, as well as leg prosthesis, and also an interactive virtual poster session that promises to be an exciting and creative event. We have already seen a lot of activity, comments and questions on social media yesterday. Keep it up today, and please share your thoughts and opinion and submit your question to our presenters via the YouTube chat. We are proud that the Cybathlon Symposium 2020 opens a new era of the Cybathlon before the main event taking place in November. We would like to gratefully acknowledge the support of our symposium partner, the Stavros Niarchos Foundation, without whom this event would not have been possible, especially in its current form as a free event open to anyone interested. Now, before Roger joins us for his welcoming remarks and a reminder on the technical aspects of our virtual format, I am pleased to first give the word to Dr. Roland Sigrist, the Executive Director of Cybathlon, for his welcome address. He will give you his perspective on the topic of the Cybathlon Symposium on promoting user-driven design and evaluation of assistive technology, and also a glimpse of what the Cybathlon Global Edition will look like.
Hi everyone, dear Cybathlon Symposium participants. I hope you are all doing well and that you enjoyed the talks at the panel discussion yesterday. Personally, I am really happy that with this year's symposium, we highlight one of the major goals of Cybathlon, user-centered design of assistive technologies. Actually, the promotion of user-centered design was a major reason why Robert Riener has initiated Cybathlon in 2013. A team can only be successful in the Cybathlon competition when a person with a disability and the developers work together from the very beginning. They need to have intensive exchange, test together, and evaluate the developments regularly. In the Cybathlon races, the devices must pass the first test in overcoming certain obstacles. However, the ultimate test is done in daily life. People with disabilities rely on a robust and functional system. Otherwise, the technology cannot be accepted and will not be used. I am very much looking forward to seeing all the teams presenting their new developments on November 13 and 14 to a global audience. We are very happy that so many teams joined the global edition, which will be new and very exciting. Our exchange and collaboration with the teams and partners is so great, and everyone involved is extremely motivated. Together, we are working towards our vision, a world without barriers. Enjoy the second day of the symposium and see you soon. Thank you.
Thank you very much for these words, Roland, and a very warm welcome also from my side to the second day of the Cybathlon Symposium 2020. My name is Roger Gassert, and I have the pleasure of guiding you through today's program together with Olivier. For those of you joining us newly today, and also as a reminder to all participants, let me provide you with a few important points about the symposium format. We are now live from Zurich again, and we'll have a mix of pre-recorded talks and live discussions. Depending on where you are watching us from, the program might be shifted by a few minutes on the YouTube stream. We will do our very best on our side to stick to the schedule. Throughout the symposium, we will have live translation in international sign language, as well as a live closed captioning service. You can activate the closed captioning in the settings of the YouTube player. Each talk will be followed by a question and answer session with our speakers joining live. So if you have questions to our speakers, please submit them via the YouTube live chat. To access this chat, follow the link to the YouTube channel provided below the live stream on our landing page. The chat will be located besides the video stream and can be accessed using a Gmail or YouTube account. Note that the chat is intended to ask questions to our speakers and not to discuss with the other participants. It will be set to slow mode and moderated by us. Alternatively, if you cannot access the chat, you can submit your questions by email to symposium@cybathlon.com. We will select questions from these two sources and address them orally to the speakers. I'd like to also provide you with some information on the poster session, which will be even more interactive today. An interactive abstract booklet is available on our landing page, so you can go through the abstracts to identify posters of interest to you before the poster session. Yesterday, posters were tweeted by the authors and retweeted on the Cybathlon Twitter channel. You can find these posters by going through the Cybathlon channel, which is also linked on our symposium landing page, or by searching for the Cybathlon Symposium hashtag. I found these posters to be beautifully designed, and I would like to extend a big thank you to all our poster presenters. You can continue to interact with the authors via Twitter today. To enable more detailed discussions and interactive demos, we will have a dedicated poster session this afternoon with Zoom rooms. A link to a page with the corresponding links for each poster and the access information will be activated during the break just before the poster session, which will take place from 3:25 to 4:05 Central European Summer Time. You do not require a Zoom account to join a meeting, but you may want to install the Zoom app on your computer or smart device. Then just follow the link to the poster of interest and feel free to switch between rooms throughout the poster session. In case we would experience technical issues, please reload the landing page of our website of the symposium to check for updates. We will now begin our scientific program and switch over to the first block of the symposium on brain-computer interfaces. We start this block with a short trailer on the brain-computer interface discipline of the Cybathlon. I now wish you a very inspiring second day of the Cybathlon Symposium 2020.
I am now very pleased to introduce our first keynote speaker of the day, Chuntai Guan. Chuntai is a professor and program director in the School of Computer Science and Engineering at Nanyang Technological University in Singapore. He is one of the leading experts in brain-computer interface research, machine learning, neural signal and image processing, as well as artificial intelligence. In particular, his research aims to apply BCI technology to the restoration and enhancement of human brain function, for example, after neurological injuries. His group is also taking part in the Cybathlon 2020 with a team that will compete in the BCI discipline. Today, his talk will be on brain-computer interface for brain function recovery in stroke rehabilitation. Chuntai, the floor is yours. Okay, so we now move to our first short talk of the day, still on the topic of brain-computer interface, which will be given by Xiaoqi Wei. Xiaoqi is a PhD student at the Brain and Behavior Lab in the Department of Computing at Imperial College London in the UK. His research interests focus on brainwave decoding and brain-computer interfaces with machine learning to help people, especially paralyzed patients, to control their surroundings using their mind. Today, he will present his research on inter-subject deep transfer learning for motor imagery EEG decoding. Xiaoqi, I pass the word to you.
Hello everyone, we're going to talk about inter-subject deep transfer learning for motor imagery EEG decoding. Brain-computer interface has emerged as a solution for people with disabilities to regain control of their surroundings. EEG signals are brainwaves directly collected from the scope, and motor imageries are brainwaves when people are thinking about moving parts of their body, like left hand or right hand. On the right shows the closed-loop control of the BCI. First, EEG signals are collected from the scope, and these signals are then fed into a decoding algorithm like CNN. The algorithm decodes the signal into commands. These commands are then used to control a real-time system like game or the wheelchair. Finally, the system gives real-time feedback to the subject, thus influencing his brain activity. Convolutional neural networks, CNNs, are powerful decoders and have been widely used for multi-imagery EEG decoding since 2015. However, the challenge here is that if we train a CNN with multiple subjects EEG with dissimilar distribution, the classification accuracy of the CNN would decrease instead of increase. This is called the negative transfer problem in machine learning. Negative transfer leads to very long tedious training period for a new user because we cannot utilize other subjects' EEG directly. There are many differences in individual EEG, like sensor locations and sensor impedance when we are setting it up, and different people have very different brain activities performing the same task. To address the problem of negative transfer, we combine transfer learning with deep EEG B-side decoding. In standard deep learning approach, we collect dozens of sessions from new subjects across different days and use these data to train a deep learning model. However, in a deep transfer learning approach, we ideally only collect one session from the target new user and then use source subject's EEG to train the deep transfer learning model. So a deep transfer learning model could be used to reduce the long, tedious training session from a new user. Transfer learning is a class of algorithms which transfer the representations and knowledge from the source domain to a target domain. In our case, from the source subjects to our new user, the target subject. There are several ways we can achieve this in the literature. The first idea is called fine-tuning. It's a naive idea where we can train a CNN with multiple source datasets first, and then retrain the CNN on a new dataset with a smaller learning rate. The second idea is to split the neural network layers for different datasets. This idea hasn't been tested for EEG decoding. On the right shows an example of the natural language processing task. We can see that different languages have a common feature extractor, and then finally, their own feature extractor was splitted at the end to deal with their own differences. Another idea is the deep domain adaptation with maximum mean discrepancy. MMD is a metric which computes the distributional distance between two distributions or datasets. We tested all three ideas in our study, but due to the time limitation, we're only going to talk about the result of the second one, which is the main result of this study. The time series EEG signals are very different from languages, so applying this idea into the EEG scenario is not straightforward. In the next few slides, we're going to talk about how we apply this idea into the EEG scenario. First of all, we use one of the best performing CNNs for multi-imagery EEG decoding in the literature as the baseline. It contains a temporal layer, a spatial layer, a mean pooling layer, and a classification layer. In this study, we proposed three architectures to perform multi-subject transfer learning. The first one is the Separate Feature Extraction Network, the SFEN. In this architecture, each individual has their own feature extractor to deal with their differences in the data, and finally, their features are fed into a common classifier to classify their multi-imagery. So after their individual feature extraction, these features have to fall into the same set of rules for the classification. Inspired by the SFEN, we further add a common feature extractor in the middle to extract common features after these individual shallow layers. And after that, we further split those deeper layers before the classification layer. So we hope those shallow layers can deal with more raw data relevant features like sensor locations and impedance, and then in deeper layers after some common feature extraction, these deeper layers can deal with more task relevance differences across different subjects. Finally, we propose the sensor aligned network, the SAN. There are two convolutional layers. The first convolutional layer acts as the channel proposal layer. It used M convolutional kernels to propose M channels, and then the second layer acts as the channel selection layers. It used W kernels to perform channel combination and channel selection. So after this layer, the feature size is W by T. T is the length of the time series, and this becomes the new input of the common feature extractor. This network is especially designed for different channel locations when we're setting up on different subjects. So hopefully after these layers, those channels can have the similar locations before they put into the same common feature extractor. We evaluate our networks on two datasets. The first is an offline dataset, the BCI Competition 428 dataset. It contains 4 multi-imageries of left hand, right hand, both feet, and tongue. We also recorded our Sabazlon BCI game dataset. The subject used relaxing to go straight, left hand multi-imagery to turn left, right hand to turn right, and use both feet to turn on the headlight. In offline sessions, the actor in the game do the correct action automatically, and we ask our subject to perform the multi-imagery accordingly. We also had a pilot online session in which the pilot tried to control the avatar in the game in real time. We trained a baseline CNN with his offline session, and he used this CNN to perform the online control. This is the result of the baseline CNN. On the left shows the average baseline accuracy of different subjects on BCI 428 dataset. We can see that the average accuracy of different subjects dropped dramatically from 82% to 73% after using all subjects dataset, instead of using only the subjects dataset. Similar result can be found on the Sabazlon dataset as well. We can see that the classification accuracy dropped from 55% to around 49% if we use more subjects EEG to train the CNN. So the baseline CNN encounters a negative transfer problem when it's trained on multiple subjects' data. However, we can see that on both offline dataset and our Sabazlon dataset, our proposed models outperform the multi-subject baseline. Note here, although our proposed models seem to be a little bit more stable, we observe no significant difference between our proposed methods and the single subject baseline. So the main information delivered here is that separating feature extractor for each individual subject could deal with the differences in the EEG data to ease the problem of negative transfer. So in conclusion, CNNs encounter decrease in accuracies when they are trained on multiple subjects EEG. And having separate feature extractors for individuals contributes to tackling this problem of negative transfer. So our proposed method have the potential to enable CNNs to utilize data from different subjects. This could reduce user training time and improve model performance. And this requires further studies. We believe this study is the first step towards using multi-subject deep transfer learning to reduce user training time. There are many aspects that we're working on. The first is to test our methods on a large data set with more subjects, because deep transfer learning is very data hungry and 5 subjects are very not enough. And the second idea is to improve network designs, like replacing fully connected layers with well-designed convolutional layers, etc. And of course, we are working towards applying our model on paralyzed end users and of course, the Sabazlon. Preprint of this study will be online soon, so welcome if you're interested to pay attention, and also welcome to email me if you have any queries, and thank you very much for listening.
We are back, and let's welcome Xiaoqi, joining us live from the UK. Welcome.
Great to see you.
All right, thanks a lot for this great talk. Now let's open the floor for questions. Maybe I'll start with the first one. So you mentioned that your method can reduce the training time. So how much do you think you can gain with that? So do you think you can go all the way to completely getting rid of training and only rely on source data, or do you still need some calibration trial always?
I think for now it still requires calibration trials because with the use of other subjects' EEG, we still rely on the personalized EEG to train a CNN decoder. So it's not very possible for now to train a universal CNN classifier for everyone.
Okay, maybe in the distant future then, right?
Perhaps.
Okay, so let's take question from the audience. We have one. Okay, so what is your opinion on using invasive approaches for BCI in the case of stroke patient? That's the wrong question, sorry. What is your opinion on using SSVEP EEG-based BCI instead of motor imagery EEG-based BCI? Since SSVEP has shown higher accuracy for BCI system, is this type of signal not more reliable?
Yeah, that's a good question. Between motor imagery and other signals like visual stimuli, we chose motor imagery because it's voluntarily controlled by the subject. Because using visual stimuli is occupying your vision, and it's not very convenient for a BCI user to control it voluntarily.
Okay, thank you very much for the answer. Do we have more questions? No. Maybe a very quick one. You mentioned in the end testing your approach on the Cybathlon. I see you also will participate in Cybathlon with the team. How does the Cybathlon scenario benefit from the approach you just presented us? Would you use that in your algorithms?
Yeah, hopefully, because considering the COVID situation, we're not able to collect much data from the subjects, and we're limited with several sessions of EEG. So maybe using other subject EEG is a good option to compensate for that. So that's the design idea behind it.
All right. Thanks a lot. Thanks again for the nice talk, and we'll close this session here. Thank you very much.
Thank you very much.
So with this, we reach the end of this BCI block. We will now have a short break before we resume with the arm prosthesis discipline.
Welcome back for the arm prosthesis block. We start this block with a short trailer with impressions of the discipline. Before I introduce the keynote talk for this block, we are excited to share another testimonial on the importance of user-centered design and evaluation with you. It is given by Maria Fossati, a designer and user of arm prosthesis, and the Cybathlon pilot for the Softhand Pro team, which will compete in November. Maria, we look forward to your statement.
Greetings everyone and welcome. I'm Maria Fossati and I will compete for the powered arm prosthesis race for the Softhand Pro team. We come from Italy, from Istituto Italiano di Tecnologia and University of Pisa. I'm really glad that I had the opportunity to start collaborating with the research team about 4 years ago, when they were developing a first prosthetic prototype from a robotic industrial end. I was involved as a user, but also as a designer, really helping in collecting experiences and suggestions to develop novel devices for assistive technologies. And with this motivation, I'm really glad to introduce you to this symposium, which focuses on user-driven processes. Today, more and more, we can see users involved in this kind of design processes, giving suggestions, experiences, and perception. This kind of processes really helps in raising awareness about disability in society. And thanks also to this initiatives such as Cybathlon, we can see more and more user design processes that helps in developing new, novel devices for assistive technologies. So once again, welcome and see you on the Cybathlon 2020 Global Edition on the 13th and 14th November. Bye.
Thank you so much, Maria, for this precious message. I now have the pleasure of introducing our keynote speaker, Antonio Bicchi. Antonio is Professor of Robotics at the University of Pisa and leads the Soft Robotics Lab for Human Cooperation and Rehabilitation at the Italian Institute of Technology in Genoa. His main research interests are in robotics, haptics, and control systems. His team participated in the Cybathlon 2016 arm prosthesis race and will compete again in the Cybathlon 2020 with the Softhand Pro. We will now hear more about the importance of softness in his talk, from collaborative robotics to prosthetics and rehab, how soft tech is changing the game. Antonio, we look forward to your talk.
Good morning. My name is Antonio Bicchi, and I'm very glad to be invited to give this keynote at the Cybathlon Symposium. The talk will be about the experience that we had in our group of using a new technologies, soft robotics technologies that we've learned throughout the years in robotics to bear upon prosthetics, and showing how this is a possible game changer for new prostheses that are better than those that exist already. So the work is joined with my colleagues and co-authors in the University of Pisa and the Italian Institute of Technology. These are some of them. It's a big group that has worked over the years. And I also want to disclose that I'm a founder and a shareholder of QB Robotics, a company that produces some of the hardware that we will see in this presentation. Let me start with the robots as they were when I was a student or in my early career as a professor. The robots were machines that had heavy mechanics, rigid, and that were very effective in making higher production and in making factories more effective. Humans were separated from machines because of their own safety. This has been very important, and today is a very important part of our economy to make better products and to make cheaper products. If you go today to factories, you will see many robots that are not separated from humans, rather they coexist, they live together, and they share the same space. Very often you see people that touch robots and robots that touch humans in a safe and comfortable way. These are called collaborative robots or cobots, and their economy is growing fast. So you see some numbers here. It's already some 30% of the market in robotics, and it's growing up quite fast. So what has changed? What happened in the meantime? If we look back again at the 60s or 70s when robotics started, a classical robot of that time, the Unimate Puma, had 160 kilo floating operations per second, which is a measure of computational power of a robot. And since then, the computational power has gone up incredibly. So 5 years ago, we had already 40,000 times that computational power in a small smartphone, and today we are more than 1 million times that computational power. So this enormous growth of computational power, of course, helped machines to do things that were impossible once. For instance, to win with the best human champion of Go, a very complex game, that was achieved in 2016 already by a machine that from Google DeepMind. So if you look now at the physics of robotics, then the same changes didn't happen. So for instance, in the 60s, the motion of robots were governed by a technology that is called servo motors, basically electromechanical systems, and still at the beginning of this century, we had a very similar technology. No such a huge change as in computational intelligence. But things have to change and are changing there too. So if you look a little bit deeper, what's the difference between the motor system of humans and the motor system of robots? The units, the basic, the elemental actuators are not that bad in artificial robots. So for instance, electric motors have a better average specific density and power density and maximum efficiency. So this is not really the point. Under these measurement, purely engineering measures, then motors can be said to outperform muscles. But if you go to more general points of view, for instance, how much does it cost to bring some mass from here to there, or how much mass has the robot to bring some payload, then robots are much worse than humans. So humans outperform robots in the sense that the system is much better than the parts. And this is shown in this cruel video to robots, where the performance of robots is shown this way. This is back in 2015, and at that time, clearly the whole system of robots was still far behind that of humans. So what has been changing, and what will change, and what is the enablers of this change? It's definitely a point in intelligence. Human intelligence is made, of course, of a big part that is computational, and it stays in the cerebral cortex. Cerebral cortex, to some extent, can be approximated with a computational model of intelligence. But if you look at the human intelligence, then we have much more than just the computational part. Indeed, the brain is nothing if it is not connected to the whole complexity of this nerve system, the peripheral, the central nervous system, and the peripheral nervous system that reaches all parts of our body, including what is under a millimeter square of our skin, already have many receptors there. And the motion of our body are also dominated by the physical distribution of many millions of muscle fibers. So it can be fairly said that intelligence is in the whole body, as much of the philosophy, engineering, and art new since the old times. In this video, you can see how the soft nature of bodies in nature are exploited by animals to do things that wouldn't be possible otherwise. The elephant's trunk doing this interesting manipulation, or the cheetah running, or the snake moving smoothly in this maze, or humans storing energy in their fights or absorbing that energy through their compliant body are examples of this. So to quote Rodney Brooks, elephants don't necessarily play Go, but have a lot of intelligence in their own bodies. Bodies are indeed soft. Our body itself is built with many muscles. Very often every articulation of our body has 2 or more muscles to make it either soft or stiff, depending on the need, depending on the task. Of course, we also have bones. We are vertebrate animals. And indeed, in the all nature evolution, we have had softness from the invertebrates to the vertebrates and to our own species. All these animals have softness in the body. So the idea of having soft bodies, bodies that can comply and that can embed some natural intelligence, has been important in robotics, and in recent years, many devices, many new robots, many inspiration have been taken from nature, as you can see in this picture, to mimic or copy or get inspired from nature. In the application that we showed at the beginning, then the transition from purely rigid industrial robotics to the collaborative robot that we have seen has been enabled also by this new attention to softness. So, for instance, these are videos that show very strongly how the new technologies allow a safer interaction of robots with humans. Soft robots have been also used to develop new robots that mimic existing animals, like invertebrates. Here is an example from Cecilia Ast and Barbara Mazzolai, or humanoids, even kids that move naturally, compliantly with the environment. So how can we use this technology, these new technologies, for prosthetics and for rehabilitation, to address some of the problems that we have as humans? We specifically focus on hands today because this is one of the parts that really make part of the physical intelligence of the human body. And it really attracts the attention of humans since the oldest times, as shown by these pictures in the autumn. So human hand indeed is a marvel of nature. We have at least 20 joints plus the palmar arches, 34 muscles, 3 nerves for the arm, and 150,000 nerve fibers just for the hand. It is a soft system that is compliant and adaptable with the environment, and crucially, it is very simple to control. When we use our hand, we don't think about the hand motion, which is though very complicated, but it's something that we use very naturally. When you lose the hand, then you realize how important the hand is to your everyday life. And since the oldest times, we have been trying to make replacements for the hands. So you have here the timeline from the ancient Egypt, first documented processes, until the innovations that were made after World War I, with Giuliano Vangetti in Italy and Ferdinand Sauerbruch in Germany, and the introduction of myographic hands in Russia in 1966. Throughout these developments, we have seen vast improvements. But if you look at the current processes that you can find in the market, you realize that they have up to 5 joints. They normally have no sensors, or sometimes they have a few. and they are rigid mechanisms, rigid machines, rigid systems. As opposed, in our hands, we have 20 joints, and we use all of them, even in a very simple power grasp operation where we want to open a jar. We have a need for the whole complexity, for the whole system. If you compare this with the existing situation, you see that it's not satisfactory. A natural, true bionic replacement needs human-like dimensionality. So in the upper limb alone, we have some 30 degrees of freedom, plus the possibility of changing our stiffness by co-contraction of different muscles to make our limbs soft or stiff depending on the task. And in the lower limb, there is a comparable complexity. How can we achieve the control and organize the complexity so that we can do things without thinking of the hand or of the foot, but doing about our daily task, simply using this complex machinery? That is a question that goes beyond the pure mechanics of implementing an artificial hand. So if you look at robot hands, for instance, already in 1986, there were hands that were close in some sense to the complexity of the human hand. Here, for instance, you have the Utah MIT dexterous hand by Steve Jacobson and others that had 16 degrees of freedom independently controlled, and that in principle approaches the human hand complexity. But it was very difficult to control and fragile, heavy, and encumbrance. The real point is to do a better technology that can make it simpler, rougher, more rugged, but also basically easier to control, making it possible for the brain to cope with the complexity of the hand. So the question is, how do people do that? How can we manage these 30 degrees of freedom in a very simple way such that a newborn can already do a grasp, such as this one that you see in this picture, without even knowing that he has hands or he has muscles? There is some theory that our group of people have come up with, which says that the whole complexity that we have in the sensory part of our body and in the motor part of our body, where we have many, many muscles and many, many sensors, are somehow managed before being dealt with by our upper level cognitive functions by some filtering, if you want, that make from a fast and abundant representation a more abstract, parsimonious representation, basically that abstracts this complexity. And the key idea of this theory is synergies. And you can regard these synergies as these funnels here that make all the complexity of sensors be simplified to some abstraction, and the motor control to be given in more compact terms and then developed in a detailed instructions that go to do the muscle structure in our body. This theory can be exemplified by the so-called postural synergies, which is a nice and simple mathematical way of explaining this concept. So it has been observed that in the use of hands, we do not control each joint independently, each of the 20 joints of our hand independently, but rather we tend to cluster them in groups that naturally act together. And the most often used group of articulations that we use together is shown here in the left, where the hand does this power grasp motion. The second synergy or second primitive of motion is shown here, where the hand opens and closes in this way. If you do the statistics of how often we use the different modes of our hands, then you find that the first synergy alone already explains 50% of the covariance of the grasp that you do every day. And if you combine the first two, already have 84% and so on and so forth. So this means that the complexity of most of the grasp that we do is not 30-dimensional, can be 1 or 2-dimensional. And this was a very important intuition that came from neuroscience, and that also has correlates in how we really control our hands. So, for instance, we have found that there are areas in the cortex that encode specific high-level representations of synergies organized topographically in the cortical areas. So there is some correspondence of this theory to the real nature of our body. But if we only focus on this mathematical description of the primitives of motion, the synergies, then things don't work out perfectly. So follow me, please, on this very simple sketch of what could happen. So take this stick hand and assume that you are closing it according to the first move. So all joints are moving together and taking on the shape that you see on the right here. That is dictated by this first mode. Then you think of grasping a ball, the simplest object, a ball. Then when you start closing the hand, you reach some point where you start having having contact with the sphere. And if you go farther, well, then the shape of the hand doesn't match the shape of the ball, of course. Maybe for some ball, yes, but most balls not, and most objects not. So what happens? The hand will not be able to grasp the object. So this observation requires that we study the problem from a different point of view. And here is something that was very interesting to observe. First of all, we do our grasps using the properties of our body, which is a soft body. It's also strong, but it's compliant. We have ligaments, we have tendons, we have muscles, and all these elements are compliant, are soft. So the idea of mixing soft robotics with the synergy model led us to propose the soft synergy model. So basically the idea is that the control that our central nervous system does acts along the primitives, those geometrical primitives of synergies that we've seen before, while the physics of our body mediate the contact with objects, so that basically our hand is following the inner image, that is the wire frame that we see in these animations, which are the intention of grasp, codified intention of grasp, while the hands follow, but also have to comply with the object and thus generate the contact forces that we need to do operations. Now, this is a nice theory, but does it hold in practice? Well, here is a very simple, interesting example or experiment that we did. Here a person is trying to catch an object which is really not there, it's an hologram. And you see that the person doesn't control the hand to match perfectly the shape of the object, rather it goes inside. We do not control the tiny details of grasping. We have the intention of grasping, and then we let the hand do the fine tuning. And if you see here, this is a picture of where the hand was controlled. Our intention was to direct the hand to go towards this position, but we relied on the existence of an object that would displace, deform our hand so that the grasp would result as we expected from our learning experience. That is what soft synergies are about. And of course, soft robotics also tells us how to build robots that look like and behave more like the human body. So, for instance, in our hands are able of doing things that the robot hands that I showed before would not ever be able. So, if you want to do this with a robot hand, forget it. It's going to destroy it. But if we build hands that have this softness inside, as shown in this video here, you can achieve a much more robust hand, still being able to do strong tasks where strength is required. So this set of ideas led us to design, a few years ago, the PIZZA IIT Soft Hand. It uses 19 joints compared to the human hand, but only has one input, because it is soft and adaptable. And here is a very first prototype of the hand that was designed at the beginning for robotic application. And as you can see that it is very compliant, can absorb impacts, and has been transformed into a prosthetic hand with long work, which is here, and you can see it here. And again, the same characteristic of being adaptable and compliant and robust. Here is a video of the hand used for the first time as a prosthetic hand. As you can see, the control comes from a usual electromyographic control, yet the hand has the full mobility of a human hand. It only has one synergy that gives the hand the intention of the user. I'm glad to introduce Maria Rosanna Fossati, who is a collaborator in our group. She does the design of the hand and also takes all the inputs from users in consideration. She is also a pilot in this assignment. And here you see another video where you can appreciate how all the joints of the hand are instrumental to let the hand shape around the objects. And not only it is strong, it is also gentle because of the way it is built according to the model of human hands. The performance in grasping and the performance in fine manipulation are not the only thing where a prosthesis is important. Our hands are very important for social interaction, for instance, when we shake a hand or simply touch another person on the shoulder. And also, it's very important how we touch our own body with our hands, something that we do very often without thinking much of it. If we want to have a prosthesis that really is embodied and feels like part of our own body, then we have also to match these abilities of the human hand. And if we look at existing classical prostheses, this is not always the case. Not even in hands that look more like human hands, but indeed, although the cosmetics are similar, the inner structure is rigid, and therefore is not compliant with the shape of our face, with the shape of our hands. Softness can introduce a degree of compliance that is much suitable for social and self-interaction. As you can see in these videos where Maria is using the hand with her own body or socially interacting with a person. And you see that this compliance allows the hand to be used in a more natural way. Here is Maria with Manuel Catalano, one of the main collaborators and authors and co-authors in this work. The first prototype of the soft hand for prosthetics that we have seen here has been tried with several partners around the world. My clinic arrives at the Ability Lab in Chicago and several others. We collected feedback from many patients, and we have realized that the soft technology has important potential, but of course we also learned many lessons as to go towards something that could become a real prosthesis for real people in the world. We are happy now that we are working towards something that can be used every day by every person with reasonable cost, good performance, and a very natural behavior. But this is not enough, and indeed we now want to go even further in the research. And to go further in the research, we have a beautiful project that I would like to share with you. Just started 1 year ago. It's called Natural Bionics, Natural Integration of Bionic Limbs via Spinal Interfacing, that has been funded by the Synergy Scheme of the ERC. as a joint with Imperial College London and Medical University of Vienna. So the goal of this new project is that of creating a fully integrated symbiotic replacement of missing or damaged parts of the human body with artificial limbs that the user will feel as true part of her or his body. Of course, to do this, we need more than just robotics. Robotics is a part of it, but we also need surgery, and we also need neural interfacing. And I'm fortunate to join Professor Oskar Assmann from the Medical University of Vienna and Professor Dario Farina, Imperial College in London, who really are among the strongest researchers in the two fields. First of all, the project aims at creating a sensory-motor interface through efferent and efferent brain innervation, creating what we call the manunculus, which is a sensory-motor image of the hand that has been amputated through targeted brain innervation of the muscles in the stump. Not just the efferent fibers, though, but also the afferent fibers will be reinnervated through these innovative surgical techniques that Professor Assmann is developing. Second part is to decode from the reading of the neural outputs through the muscles what the language of the spine is, so that we have a better understanding of what the intention of motion of the patients are, and also how to convey back our information from the prosthesis to the patient. And this is where Professor Farina. As to robotics, it is important to note that once we will have this manunculus, this sensory motor biohub image in the stump, then we have to connect the motion lens that our brain will send to the hand with the feedback that we had from the object. And here it is important to notice that this feedback is generated through the interaction of the hand with the environment. And it is an important thing for humans, for us to believe that some parts of the body are indeed parts of the body, that the expectation of the feedback from the interaction matches what we had learned in the past. So if we want the prosthesis to be felt as part of the body, it is important that what we get back from the interaction is similar to what we do back from the interaction of our real hand. And our real hand is soft. So we believe that it is important that prosthesis is also soft, mechanically close to the hand that is replacing. And this, of course, is our job in this project. Here are some first results of this natural bionic project that will go further in 5 years more, so we are at the very beginning. And here is the new hand that is looking like human and interacting with our body in a natural way. Here is also social interaction of the new hand. And in this video you can see again Maria using a first prototype of the new natural bionic hand and showing how the compliance of the hand, the design of the hand, the control of the hand, the very natural control of the hand, allow her to do things differently from conventional prosthetics. Well, of course, not saying that it's definitely better or worse, it's different. And that's the point of this talk. It's a different approach to prosthetics that we hope will bring some improvements. Of course, the control of the prosthesis is not the whole story. We also have to give feedback. And feedback is very important. For instance, I just already mentioned that under a cube millimeter of our skin, there are many receptors. And if you look at the nerve fibers, as Professor Assmann has done, that go through our arm, you realize that out of the 350,000 axons that innervate the human arm, only 10% are efferent. That means 10% are those that control the motor units in our body. 90% is afferent, means 90% is dedicated to bringing sensory feedback to the spine and cortex. And this observation is also possible to see that, as Professor Hasselman says, movement is mainly a sensory phenomenon. 90% of our nervous fibers are dedicated to sensory. And in what sense this is true? For instance, in our facial muscles, we have, it is known that anatomically we have no intrinsic sensors, but we have sensors on the skin of the face, and those are enough to control our face. So these are examples of how important sensing is to the control of movement. In this project, we will have a transplant of the dermis on the part of the stump where the homunculus will be made, and through suitable devices, we will then have stimulated these dermal transplants that have a rich innervation, a rich equipment of receptors, re-innervated through the surgical technique, and we will have to stimulate. Of course, there are several ways of giving feedback from the prosthesis where tactile sensors are placed to our nervous system. And here are a few systems that have been tried in the literature. Most of them are invasive. They go through needles or other means to the nerve. The approach in this project is different. What we want to do is rather to use non-invasive feedback. And here is a very first prototype of the prosthetic hand with a display device that eventually will be used on the homunculus, where the dermis transplant is there, to provide this image directly to the spine. So sensory feedback, as we said before, is no less complex than what we have in the motor domain. And it is observed that humans use nearly instantaneous means for reducing the dimensionality of the elementary sensory inputs through those invariants or synergies, as we called them before, and also priors. So it is important here to have a theory, and we have been working in the past to understand better what this means. So, for instance, one important thing is that we have intrinsically the ability to be tricked by our perception. We have many illusions, perceptual illusions that can be exploited. So a perceptual illusion, for instance, is shown here. On the left, you have the barber pole illusion, where you have something that is, this pole is really rotating, but it appears to you and me as moving upwards. What is happening? We are extracting from this image some primitives of motion that are abstracted from the reality, and therefore they project reality on a lower dimensional space where we can be tricked. And indeed we get a wrong idea. So our approach is, why don't we try to exploit these weaknesses of our sensory system and make it possible to deliver perceptual cues without rendering the whole complexity of the tens of thousands of receptors, but rather going to a more abstract, more parsimonious representation. The same illusions are not only in vision, but also in tactile motion. Therefore, we hope that we can do something about that, and we already have implemented devices that display tactile information in a more simple way. Also, other observations are that when we have this distribution of sensors in the skin, as I said, this is very important to detect motion. So if I want to find where my hand is, I basically mostly use sensors that are distributed in my skin, and they're not distributed randomly. Neither they are distributed uniformly. There are reasons why they are more dense in some parts of the hand and why they are less dense in other parts of the hand. If we understand this principle, then we can build better devices that can, for instance, show the person, as in this preliminary experiment here, when the object is touching the hand, and therefore the person can control much better the grasp of the hand. Okay, now time to come to Cybertron, this exciting adventure that we have joined already in 2016, and that we will join again this year. We've learned a lot through interaction with other teams, through the competition, and through the social living together in this occurrence. I think that Cybertron is really a great idea. This Formula One of Paralympics, as I call it, what is really changing the panorama in the paradigm in prosthetics. So here is our participation to the series in 2019, where the SoftPen Pro was used by Maria as one of our pilots, and you can see some of the operations. Now you will see many of these in the next in the coming days, so I will not insist too much on these tasks. Just briefly mention that in the series that we had in Karlsruhe, Maria did very well. She ended up second, and also Rosa, other pilot, did very well. She was only 4 seconds lower, but did the whole task completely. Of course, we were the only research hand in that competition. We lost to Osur, that has a very effective hand and very well proven in time and with patients. But we hope that we will do even better this year. Here is Rosa, that I would like to introduce to you. And besides the actual results of the competition, I was very happy of being part of Cybertron because of the many lessons that we learned, not only during the race, but also after the race. So here are some picks that we took without the pilots knowing. And here is, for instance, Maria using the hand to manipulate her cell phone or to open a bottle of soda. And if you look at this close-up view, then you realize that Maria is really using all 19 joints of the hand, although the control is very simple. And this is very much like what the normal hand does in the left picture. So this is a proof that even though the controller of the hand remains very simple, the intelligence that is embodied in the hand itself allows a more natural interaction. Here are some self-interaction examples where Maria and Rosa were waiting rather nervously for the start. You see that they use the hand in a pretty normal way, like we would do with our own hands. Rosa that is working on her knuckles just to get concentration. Rosa makes fun with the hand, and Maria tries even to dance with an engineer, with Manuel Barbarossa, who is an important part of our team. You do these things if you have a hand that can comply, if you have a hand that can interact normally with other people's hands. You are encouraged to do so at least. And Maria doing a massage, interacting nicely, safely, softly with Cristina Piazza's body. Cristina is one of the leaders of our team at this Cybertron. And finally here Maria, after a year or two, doing something that no other prosthetists can do, I believe. Maybe not so useful, but funny. So this is work that has been done by a large group of people. I'm indebted to all of them, and I really hope that I show throughout this talk that soft technologies are a new perspective that can bring some innovation and some useful new features to prosthetics. Thank you very much for your attention. here is Rosa and Clint also saying goodbye that way. Thank you very much.
We now welcome Antonio live here with us from Italy. Antonio, thank you very much for this insightful talk, and especially for reminding us that movement is always strongly interconnected with sensory feedback.
Yes.
So we now have time for some questions from the audience. Yes, our human hand is much more complex than any prosthesis can be. Therefore, shouldn't we aim to build more specific prostheses dedicated to specific tasks only? One user would use many.
That's a possible avenue. I'm not sure. We do use tools for different tasks. Normally, we use the same hand with tools, and this idea could be similar to changing the hand, if I understand, as if it were a tool. I'm not completely sure that most users would embrace that point of view, but some could. Why not?
Okay. A further question is, in the long run, do you see prosthetic research being overtaken by regenerative limb research?
I must say that I'm not able to answer to this scientifically. I know very little of regenerative medicine. I haven't seen so far results that encourage us to think that we will see this in our lifetime. So maybe in the future, but rather far future.
So it's worth continuing to improve the technologies we're working on right now.
I would think so, yes.
Okay, do we have further questions? How much more important is the look of a hand rather than functionality when talking to the users?
Well, the look of the hands is it's not an easy point. Every user has a different point of view, and we have, for instance, learned that the old approach of making it very much like the human look is not always the best. Of course, everybody knows that in many cases, people with amputations don't want to conceal the technology that is behind, but instead are proud. So, for instance, one of the roles of Maria that you've seen before, who is a designer, is exactly that of studying what the users really want. And the users are many. It's not one. It's not few. It's different types of people. The younger, the elder, and each group has its own preferences. And the design of the looks is very important to make it acceptable. Functionality is also very important, of course. And as I said, not just the mere grasping power or dexterity in operation, but also the naturalness of self and social interaction, we believe.
Okay, thank you. Do we have time for one more question? What does it mean to Rosa and Maria to experience the kind of hands you are developing? What kind of feedback do you get from them?
Both Maria and Rosa are our pilots, our preferred users. They're part of the team. So I'm glad to say that they're happy to use it, of course. They're enthusiastic of using it. More than this, I can say that we have tried probably several tens of users, with several tens of users, and the feedback that we got is almost invariably very good. We only had a very, very few, I can remember one user that was unhappy about these different features of the hand. It's normally well received. The hand is not just looking naturally, it's functioning more naturally, and that is much appreciated. So I would say that the user reception, the way they receive it is very good.
Okay. Now, nevertheless, if they are very happy, I'm guessing, do they still have some desires that you could address in the next iteration? Some things they think that are lacking right now?
Of course, there are many. So many directions of development. As I say, that we have learned a lot from users, and we have changed already the design, but we have still a long way to go. From details, like the hand is still a bit noisy, like many hands, and that should be eliminated. To more dexterity, we are now working on a more dexterous hand with more than one control, and integration with wrist and possibly with an elbow. And definitely the sensory feedback, which is one of the topics where we are working very, very hard now.
Okay, thank you very much, Antonio. We have to close our live discussion here, but you will now join the chat and address the remaining questions. Thank you so much for being with us today, and good luck with your team at the Cybathon 2020.
Great pleasure, great pleasure.
Thank you, Antonio.
Thank you, everybody.
We now move to the short talk in the arm prosthesis block, given by Nathanael Charasset. Nathanael is a permanent research scientist at the Institute of Intelligent Systems and Robotics of the Sorbonne Université, Paris, working in the AGATE team. He previously was an associate researcher at the Human Robotics Group at Imperial College London. Nathanael received his PhD from UPMC and holds an MSc degree in mechanical engineering and also an MSc degree in robotics. His research aims at understanding and improving physical-human-robot interaction for neuromotor rehabilitation and assistance. Nathanael is part of the Smart Arm team, which will compete in the Cybathlon 2020. Nathanael will present to us on behalf of Mathilde Legrand, who is currently on maternity leave. Nathanael, we look forward to your talk.
Hi everyone. Thanks to the organizer for letting us presenting our work today at the Cybathlon Symposium. I will be presenting the work of Mathilde Legrand, who is a PhD student that I supervise with Guillaume Morel, and who is actually on her maternity leaves. So we are all members of the team Smart Arm, SAM, from Sorbonne Université in Paris, France, and we will participate to the Powered Arm race of the Cybathlon 2020 Global Editions in mid-November. Our teams gather some roboticists, neuroscientists and clinicians around one pilot, Christophe Huchet, who is an arm amputee. The specificity of our team is that we focus on the development of improved prosthesis and improved control approaches for high-level amputations such as arm or shoulder amputation. So when we look at the current mechatronics of upper limb prosthesis, what we can observe is that the mechatronics is very advanced. It is possible to find some commercially available FDA-approved polydigital hand prosthesis, such as the iLimb Ultra from Touch Bionics Saussure, the Michelangelo from Motobok, or even wall robotic complex arm prosthesis, such as the Look Arm from DEKA. But yet, there is a discrepancy between how advanced the mechatronics is and how simple and limited and constraining the control approaches of these devices are. So what kind of control really exists for those advanced devices? We try to look at and to give an overview of the kind of control family that exists. So the most common control approaches to pilot a prosthesis are called direct control approaches. Basically, a user who wants to reach a target X will have to simultaneously control his own body, his thumb, and the prosthesis to be able to perform a combined adequate gesture. So to do so, the most common approaches is to measure on the user body an auxiliary signals that would be produced by the users and that will be used as a control input for the prosthesis joints. Different kind of signals can be used, but usually electromyograms are used, whether it's simple contraction or more complex muscle contraction patterns as an input. It can be also some signals from the central nervous system, like electroencephalograms, or more simple signals such as some human joints displacements that can be used as joysticks, for example, the head movements or the ankle movements that will be used as signal input to control some joints of the prosthetics. But what is important to observe is that this kind of control architecture, the direct control architecture, creates a dual control loop and a dual task for the users. The users has to produce an auxiliary signals that will be used within the prosthetic control loop to move the prosthetic joints, and at the same time to naturally control his own body, to combine those to perform the desired trajectory X. The problem is that those two loops are very different. The prosthetic control loops being slow and complex to use because of the generation of, for example, muscle contraction. And the result is the following one. When a user amputated, for example, a transhumeral amputee, here with an osseointegration, is using a myoelectric control prosthetics to perform a reaching task, what you can observe is that while the myoelectric control is used at the beginning to positionate, orient the arm, when there is a final reaching error, instead of using the control loop of the prosthetic, the user prefers to use the body control loop to naturally compensate, to exhibit a body compensation to solve the final positioning error of the prosthetic hand. One possibility to solve this issue of the dual control, the dual loop paradigm, is to use, for example, joint synergy-based approaches. Synergies or inter-joint coordinations are basically a way the central nervous system has to manage the body redundancy and to solve this body redundancy to perform some tasks. So, for example, during a reaching task, there is usually a relationship between the shoulder velocity and the elbow velocity. Those kind of synergy of relationship can be modeled and used in a specific control where basically instead of producing an additional auxiliary signal, the movement of the body of the users is used through a model to automatically compute the velocity that the prosthetics should exhibit to reproduce this kind of synergy. So in this case, for example, the elbow prosthetics will be automatically piloted by the shoulder velocity of the user to reduce the complexity of the control. The problem is that such approach is complex to set up. First, building a proper model of the synergy is difficult and needs lots of personalization on each subject, but more problematically, basically synergies are task dependent, meaning that the control architecture would be very complex. It would have to recognize the kind of task being done to load the proper synergy model to be able to control the prosthetics in a correct way. So more than this, there is a fundamental issue with these approaches. Basically, they are open loop approaches, open loop from the robotic point of view, meaning that in both cases, the correction, the loop closing has to be done by the user through his human sensory system, through visual feedback that is heavy and cumbersome, and he has to realize that and to perform an action to correct the prosthetics. The prosthetic is not able to close the loop because it has no idea of the task, of the goal, of an error to servo its behavior onto. So the result is that because of the discrepancy between the loops and the complexity of using the prosthetic loops, the users tend rather to correct an error of the prosthetics by using body compensation because of the motor slacking behavior, the slacking behavior of the motor control of the central nervous system. Basically, people will exhibit some body compensation. They will use, thanks to body redundancy, some proximal joint motion such as shoulder back movements to compensate for the prosthesis error rather than using the prosthetic scheme. So what we propose is basically to take advantage of this behavior, natural behavior, and to build a control that use this body compensation. We call it compensation cancellation control, or CCC, and this is an overview of it. I'm going to rotate the scheme for more clarity. In 3 steps, we measure in the user body posture, and we compare the posture of the user body to a reference, what we call non-compensatory posture. This is used to compute an error that is then transformed into a velocity of the prosthetic joints. More simply, the user is in charge of controlling the prosthetic displacement, the end effector displacement, and the prosthesis is in charge of changing the kinematic structure of the prosthesis to minimize the body compensation from the users. For example, to reach a target with an elbow, when the elbow is fixed, the user will compensate with his trunk. The idea is to measure this compensation and to use it to change the kinematic configuration of the elbow to avoid the user to reach the object while staying in a compensatory posture. This is a very natural approach because there's no specific learning. The body compensations are naturally and unconsciously exhibited by the central nervous system. It's versatile because the non-compensatory posture, the reference use, is not task-based. Yet it has some limitation. It can only be used to control positioning and orienting joints of the prosthetics and not the grasping or the hand, because there's no compensatory posture of the grasping that can be used and can be tracked to determine that the user wants to close the hand over one object. So at the moment, we are working on how to map the compensation onto the device motion, and also on the definition of what is a compensatory posture, and how to maybe modulate it, not to have it fixed and to have it evolving according to the environment or to some preference of the user. So what I'm going to present very quickly here is the first feasibility study that we performed with an arm amputee wearing a trade-off active degrees of freedom active prosthesis with an active elbow, wrist and hand, who performed a Rowellian clothespin test, so to move some clothespin from one horizontal rod to a vertical one. And he used for that the CCC, the compensation and cancellation control mode, to control the elbow and the wrist, while the hand was always controlled with myoelectric control. And we compare that to the case where a conventional myoelectric control was used with a conventional co-contraction switch to pilot all the joints together with the same muscle contraction signals. What we observe is that CCC allows a reduction of the task. It reduces the user engagement and the mental burden required to perform the task, measured through the NASA TLX score. Also, we observed an increased use of the prosthetic joints with this control mode, but yet there is one issue that we observe, is that the CCC tends to enhance the body compensation, which is not acceptable. So we are at the moment working on improved tuning or more training of the users to be able to minimize those trunk compensation especially. So in conclusion, those are encouraging results. We are currently working on theoretical proof of the kind of stability of this specific human-robot coupling. We're working on controlling simultaneously more degrees of freedom, having a generic way of formulating our controller. And later on, we believe that we could be able to apply this kind of approach to other assistive devices, such as exoskeleton. So I'm going to thank you, and I will be happy to answer some of your questions if you have some. Thank you very much.
We now welcome Nathanael live from Paris. Nathanael, thanks for being with us this afternoon.
Thank you very much.
Nathanael, I'd like to immediately start with the first question. So you showed us some objective and semi-objective metrics for how the behavior changed with your compensation, if I can say, the strategy that you implemented. And you showed that the time reduced, and also that on the NASA TLX that the scores reduced. But you also mentioned that the compensation increased, compensational movements increased. What kind of subjective feedback did you get from the test user? How was this? How did this feel to him? How did he react to what the prosthesis did?
Thank you for the question. The user was really happy with this system because the use of myoelectric to control several joints requires a lot of co-contraction. And co-contraction, depending on the stump and the muscle quality of users, can be very difficult to produce. And in our case, our participant has a lot of difficulty to exhibit proper co-contraction, so it was very fatiguing at the muscle level. So being able to perform the task to use different joints without having to regularly exhibit co-contraction was a real pleasure to the participant. Additionally, his description is that the device felt natural because, of course, the compensation in this case was quite extended and enhanced, but he was not he was not really aware. I mean, he believed that he was not doing something new, some new skill, and hasn't been learned to be able to perform something with the prosthetic. And this was very pleasant for him compared to the time it takes usually to be able just to master simple myoelectric. So they were saying that still some work has to be done, but they were very well surprised by the system.
So do you think that the collaboration, let's say, between the prosthetic limb and the user would further increase if there was more training? Is it a question of the amount of training to get to better know the behavior?
Yes, definitely. Because as you may have seen, in our control scheme at the moment, there is a specific and very crucial integrator, meaning that there's some kind of inertia between the compensatory exhibition and the reaction of the device. This allows actually to have not a rigid coupling from one joint moving another that would be constraining, but this kind of integrator necessitates a bit of use to kind of anticipate the body compensation action that would lead to the prosthesis reaction. So for sure, with more time, with more adequate possibility tuning of the gain, we could definitely have faster subjects and limited compensatory compensation exhibition.
Thank you. Let's see if we have a question from the audience. Interesting talk. Were some aspects of NASA TLX improved more than others, thanks to your control strategy?
That's a very good question. Unfortunately, I don't have access or to the specific detail of the results, and Mathilde could have answered to that, but I can't. Hopefully, we will try to provide some information within the next paper, or don't hesitate to send us an email. We can provide some of the more insight later.
Thank you. Do we have further question? Okay, I'll go on one more. You underlined the importance of this joint control for above elbow amputees. And when seeing what you presented, I was wondering, could this same strategy also be used for prostheses that have an active wrist? Because having an active wrist or not also can induce additional compensatory movements.
Definitely. That's our next step. So yet we tend to use existing commercial devices to be able to quickly do experiments with patients, but there's yet no. There's a very limited number of active wrist flexor that are available. So we have built ours, and the next step is to make some trials on a more complex prosthesis that was developed at ISIR that has 4 degrees of freedom, excluding the hand, so that integrate the internal external rotation for the shoulder, the elbow, and to doff at the wrist, because as you said, the wrist flexion is critical. Yet at the moment, transhumeral amputees tend to orient their hand with their shoulder and elbow complex, with lots of adjustment like that. That is problematic from an ergonomic point of view. So that's our next goal.
Okay, thank you very much, Nathanael. We have to close the live Q&A here. If it's possible for you, it would be great if you can also join the chat and see if there are any further questions there. Thanks so much for being with us this afternoon.
Thank you very much.
We will now have a short break and then continue with the interactive poster session at 3:25 Central European Summer Time. I kindly ask all presenters to now prepare their Zoom rooms and interactive demos so that we can start on time. To access the Zoom rooms, please follow the links that have now been activated on the symposium landing page. Please don't forget to reload the landing page if you're already on that page so that you can see the links appear. You will also find a direct link on the slide that will be shown on this stream during the poster session. Please feel free to visit several rooms and interact with the presenters. We wish you an engaging and inspiring poster session and stimulating discussions.
Welcome back, everyone. So I hope you enjoyed the poster session as much as I did. I visited a few of the Zoom rooms, and I was extremely impressed by the creativity of everyone in preparing interactive material to showcase their work, and in that sense taking full advantage of the virtual format of our event. Very well done, and congratulations to all our poster presenters. If you did not get the chance to visit everyone's Zoom room, don't hesitate to contact poster presenters on Twitter or via email after the end of our symposium. Now it is time to start the next block of presentation on the topic of leg prosthesis. Here's a short clip for you. So time to welcome our last keynote speaker of this Cybathlon Symposium 2020, Helen Wang. Helen received the MSc and PhD degrees from Arizona State University, and she is now the Jackson Family Distinguished Professor in the Joint Department of Biomedical Engineering and a Director of the Closed Loop Engineering for Advanced Rehabilitation Core, or in short, CLEAR, at North Carolina State University and the University of North Carolina at Chapel Hill in the United States. Her research focuses on neural machine interfaces, control of wearable robots, wearer-robot interaction, as well as co-adaptation, with clear application to assistive devices such as prosthesis. Her talk today will be about neural control of robotic prosthesis. Helen, we are looking forward to your talk.
So first, I want to thank the committee for inviting me to give a talk at the Cybathlon Symposium. My name is Helen Huang, so I'm going to talk about my research related to neural control of robotic lower limb prosthesis. Just a little bit about myself. I am a professor in the Joint Department of Biomedical Engineering at NC State University and UNC Chapel Hill. I am also the director for CLEAR Core. So CLEAR stands for Closed Loop Engineering for Advanced Rehabilitation. So this is basically a group of faculty who share the common interest in rehabilitation engineering and science, as well as clinical translation of the research. So I highly encourage you to view our website and see what we do in North Carolina. Okay, also I wanted to highlight one Cybathlon team from our own department, PAC Bionics. This is a team. They will compete the power leg category. So the team is composed of a group of undergrad students. So most of them are senior now. So when I talked to them about the opportunity to compete in Cybathlon, they were just a sophomore. Very proud of the student who has grown so fast in the recent 2 years working on this project. So the team leader is Dr. Bruce Wigan. He also received a PhD from our program a couple of years ago. And I also wanted to highlight the two awesome pilots in the team, Charles Humphrey and Faisal Hamadoun. Both of them has spent a lot of time with the student. So I look forward to the event and then cheer for the team. Just back to my own research. So I lead a group of students and engineers who are working on robotic assistive device. So our focus is trying to merge human and these wearable robots, not only physically attached together, but also function as one. So we call them a human-robot symbiosis. So our goal is to use this technology to improve quality of life for people with a disability. Specifically, we work on neural machine interface for not only prosthetic leg, but also prosthetic arm. We work on control, automation, artificial intelligence for operating these wearable robots. And we also conduct the research trying to understand how human and these wearable robots interact with each other and co-adapt. So in this talk, I will mainly focus on robotic lower limb prosthesis. I want to present to you how I can achieve human prosthesis symbiosis through neural control. So addressing the quality of life for individual has a limb amputation has a profound societal impact because this population is large and growing. So in the US, about 2 million individuals live with limb loss. And globally, there are about more than 1 million limb amputation are performed each year. So majority of the limb amputation are performed in the lower limb, and many of the patients depend on some sort of assistive device, such as a prosthesis, to restore the basic mobility, basic activity of daily living. So when we look at the market in terms of lower limb prosthetics, majority of the devices are still passive. However, with the advances in sensors, actuators, and also battery, so develop these robotic motorized prosthesis, lower limb prosthetics, is very feasible. Actually, this line of research actually has been ongoing for more than, I would say, 15 years. So on the top line here, you will see is actually an older version prototype or commercial device that's available about 10 years ago. I have been using these for my slides for many years. And then I want to highlight the two commercial devices. One is the Power Knee. This is the first version from Author. And then this one is the Biome, currently called InPower, owned by Ottobock. And then there are recently, even right now, there are some multiple new prototype is developed. And I apologize that I did not including everyone's prototype. So that these new generations are more powerful, reliable, lighter, and practical. So this is definitely a promising future and then the promising technology to further improve the mobility for individual has a lower limb amputation. So all these devices, robotic device, use some sort of autonomous control. So here just showing a very typical way, the typical control for this device. So it is combined with a finite state machine with the impedance control. So finite state machine basically identify the human's state during the gait cycle. And then based on that information, then we describe what is the desired behavior this device is supposed to do. And then we use the impedance control to achieve that. The benefit of this device is it powers through the entire gait cycle and then being able to generate a gait pattern very close to what we observe in able-bodied person's intact limb. So here I show this circle. This circle represents this state machine. And then as long as we can predefine this task, then this potentially can enhance, and then the power device would be able to assist the person to walk on this terrain. And then for power device, it's probably more important and useful for tasks like stair ascent, because in this case, we need more power from the lower limb joints. Again, once we can predefine this locomotion behavior, and then we can include that into the controller, then this became a part of the control as well to assist the person to perform this locomotion task. And then we can continue expanding. The problem of this control is, well, it's a lack of adaptation. So it's a lack of adaptation to environment, to the user's physical condition, movement intent, and the lack of ability to support activity that is hard to predefine. Well, so this control, for the robotic prosthesis control, which is a machine control. They are known to be, fast in terms of a feedback control rate. They have a faster actuator and then more precise sensor that they could provide a precise control if this task is well defined. Okay. However, they lack adaptability. But if we look at another controller within this human prosthesis system, that will be the human motor control. We know human motor control is highly adaptable, flexible. They can generate versatile motor behavior to adapt all kinds of environment and activity. So in order to generate or improve the function of these prostheses, one way we can achieve this human prosthesis symbiosis, so basically the two systems can work together, is building this neural interface. Let the two controllers communicate with each other directly. So therefore, I'm going to show you a couple of studies that I have been carried out around this idea. So my goal is to enabling versatility of robotic leg via neural control. So versatility here, what I define is a prosthetic device that can adapt to many different environments and activity in the individual's daily life. So I have been working on this topic for a couple of years. I will show you two main concepts that I have pursued in the past maybe 12, 15 years. So my first project related to this topic is it came from my understanding of how current these prosthesis is controlled. So I talk about these locomotion mode, right? So each individual predefined movement behavior that is associated with different locomotion mode. And one important aspect is you have to make this task transition in order to transit from level ground walking to stair ascent, for example. So this is a very early version of the video. This is actually the first version of the power knee. And then this person is demonstrating, transition from level ground walking to stair ascent. So the device has no idea what is in front of the person. So what a company did is they have another sensor attached to the sound side, and they use some sort of a special body motion, as well as the motion from the sound side to trigger to tell this prosthesis, well, the next step gonna be stair ascent. And this approach is sometimes not very reliable. And then also later the company actually removed the intact side sensor and then started to just trying to teach the user how to loading appropriately using some body motion, and then they can trigger this transition. So to me, I was thinking, instead of using this body motion, how about just decoding their neural intent? And then the person would be able to transit the task seamlessly. So that's exactly what I did. So I came up with generating this supervised control approach. So I would generate a neural machine interface on the top as a higher level control that identify users' locomotion mode. And in the lower level control, it's still those autonomous control, right? So you predefined the locomotion behavior. And then when the neural machine interface recognizes the intent, then they will select appropriate mode. So initially I used the input, which is the EMG came from the residual muscle, and then I developed the phase-dependent strategy. And then later I also use additional sensor, which is called the neuromuscular mechanical fusion. So I also fusing some additional sensors, such as the sensor that monitor the motion of the side or loading on the pylon, and then integrate together And I built a classifier that could be able to recognize what a person's next step will be in terms of locomotion mode. I'm not going to talk too much detail. So if you're interested, you can view some of my paper early on decades ago which has a very detailed engineering approach there. All right, so fast forward, we did the decoder and we connected with the lower level finite state machine. And here is just the lab testing, and we can see that the user would be able to just walk towards stairs and then transit without stopping or doing any like the appropriate loading. And then, so the transition is smooth. Well, this is great, but every time when I presented this work, while I'm working on this idea, I often get a question regarding, is your decoder has error? And then I said, yes, always there's like 2 or 5% of the error. And does that mean there's a 5% chance that person actually gonna fall? This is a great question. This is also highlighted the difference between prosthetic arm and the leg. So for lower limb device, because the basic function is basically supporting the upright balance stability, when there's an error happen, then potentially the person might fall and generate injury. So that's a safety issue. But does the neural control error really lead to the person fall? I really don't know. So therefore, I conduct another testing. I simulated error while the person walking. This error is often what I saw during my locomotion mode recognition algorithm. And so for this 2 video, just look at the flash of this arrow, the word, the text. That is the duration when arrow was injected. So here shows some of the arrow like this one. And you can see this arrow, you barely can see the difference of that cycle versus other cycle. And then more important, the user also report they feel nothing. So this arrow doesn't really cause any danger or problem. So we call it a non-critical error. But we also have a situation like this one. So you see the hyperextension. So there's one more time. And then there's in the middle of the stance, there's a hyperextension that's generated that definitely caused the balance index we measured has perturbed. And the user also told us that they felt like not comfortable walking with it, feel not safe, not stable while walking with it. So those are critical errors. When we put these arrows together and then we map the arrow, is when the arrow happened and how big is the arrow cause the mechanical work change around the knee joint, versus the response of the person in terms of balance stability. Here shows angular momentum, and you can see that not every arrow gonna cause the problem. Okay, and also for the arrow happen during the swing phase, even though the magnitude is large, but it's okay. But during the stance phase, humans are more sensitive towards the arrow. Okay, so how do we, so in the future work, how do we dealing with these critical error? Is important in order to make this practical for user to use. All right, so the previous approach that has allowed terrain adaptation, right, level ground, stairs, and ramp. But when I revisit my goal, the versatility is adaptation to many different environments and activity. How about the environment like rocky trail, or activity like play a tennis or dance, or potentially let the amputee to compete in a Ninja Warrior, which is a popular TV show in the US. So when I look at this supervised neural control I mentioned previously, so I realized the behavior of the prosthetic joint is still dominated by this autonomous control. Even though we have a neural interface, but we would not be able to use this interface to operate the prosthesis to perform tasks that is beyond what is predefined here. But my goal is truly to give a human a freedom to be able to use this power device to assist all kind of activity, including those activities not that, easy to predefine motor behavior, such as like a pre-tennis or competing or jumping or freestyle dancing. So can we do that? Back to this diagram. So again, we have a two controller, human motor control and the machine control. So we mentioned that the one way we can merge them together is through neural interface. But instead of directly connect this two, maybe we can let the neural control dominate. So for example, in this case, we can use the residual agonist-antagonist muscle pair for the ankle control to directly operate the prosthetic joint. So the ankle's behavior is purely dependent on the neural input came from the human. So now the main question is, the first question, although looks very fundamental, but is critical, is can amputee coordinate their residual muscles in an appropriate way for the continuous and direct EMG control? So this is important because EMG is the control source. If the user cannot produce appropriate co-activation, then this approach would not work. And also we want this approach to be reliable as well. So in order to address this question, so my group has conducted a sequence of study. So the first one as an example here is we take the EMG signal from the residual TA, tibialis anterior, and residual gastrocnemius, and then we map the magnitude into 2D space. So the vertical line is the magnitude of TA, and the horizontal is the gastra. So this marker or cursor, okay, so once it's reaching a certain space, it colored blue color in the space. And then every spot, the cursor is representing the co-activation pattern across the two muscles in a real time. So the task for the user is trying to color this space as many space as they can. Another example, we use the same residual muscle pair to proportionally driving the torque applied on this invert pendulum. So the goal of the user is basically trying to balance using the residual muscles to balance this invert pendulum to the vertical place. Well, due to the time limit, I won't go over every detail, but it's a really interesting, a lot of interesting observations. So I encourage you to read our recent work. So I just want to highlight the two take-home messages. So one is that there's a large variation across amputee in terms of their capability to co-activate the residual muscle. So example, so we grouped the patients into three groups. And then in the group one, so we have a subject that would be able to feel more than 85% of the 2D space. So that means the person would very flexible be able to generate a lot of co-activation patterns in this space. And then the second group has a majority of the patient in this group. They have a co-activation, some level of co-activation, but it's smaller than the group one. And then the last group, we have two patients who has a very limited co-activation. So they basically can active one muscle at a time. So you can see these lines, it means one muscle active at a time. There's no much co-activation in the other space. So the second take-home message will be, if this muscle, residual muscle, is in context of a control, such as this control of invert pendulum, they see the consequence of their muscle activation after a certain amount of a practice. It's actually not very long, so we gave a 10 trial of a practice for each person. And the majority of the patients, so basically in the patients in group 1 and 2, being able to adapt their residual muscle activity for the efficient control of this invert pendulum. So they started to shaping their control, the EMG co-activation, and then be able to perform the task more successfully and efficiently. So this result give us a confidence that if this residual muscle has a certain meaning, so in terms of control, right? So they can control a prosthetic leg. And then also if we give a certain amount of time for practice, they would probably be able to use those devices for their activity performance. But is that true? So first, instead of let our subject to compete in a Ninja Warrior, we actually let them to first to just try to control their posture. So why one is a posture control is very important. It's happening like in almost every activity upright. And then 2 is based on our knowledge, none of the power device or passive device would be actively support. This device can actively support their posture control. And then also, if someone say, how about using autonomous control? Usually this is quite difficult. So there's an anticipatory part, without even contact, the user started to modulating their joints. That's very difficult for autonomous control to do. And then for tasks like this, for example, in order to control the torque on the ankle, you have to know, how heavy is the box, how compliant is the ground the person stand on. Usually those information is harder to obtain. So anyway, so we did a case study. So we only recruited one person, go through a couple of weeks of training. So the setup is straightforward. So again, we have residual TA and the gastra. We got the magnitude. We use the magnitude proportionally driven this pneumatic muscle actuator. So how it works is when it's active, it will shorten and generate force. So just like a muscle. So we call it artificial muscle or pneumatic muscle. So there are 2 from the 2 in the front mimic the function of TA, and the 2 on the back is mimic the function of gastra. And then we select one patient from group 2 because again, majority of the patients will have a profile like that. If they can do it, so group 1 should be no problem to use the device as well. So the procedure is we introduce him to understand, right? So when the muscle contract, how that will operate the prosthesis. Then after that, we went through a 4-week PT guided training and evaluation for posture control. So here I wanted to demonstrate how it will work. That this is the early on trial, the first day. He is the first time being able to perform this task, which is pick up this heavy medicine ball and put on the side, so weight transfer. I want you to pay attention to how he controlled this joint. So he could be able to bend really low. And you see that little bit kick there?
Literally, to say, okay, that's so much down, together.
Okay, you can see when he's very excited because he would be able to successfully finish the task, be able to without causing any dangerous situation. And then two is he also mentioned that he has to control it, and sometimes it's too fast, faster than the intact side. This is early on, but later, actually, we see a synchronization of the two limbs. So that's no longer true. Later, he actually don't really think that much anymore. So very interesting, I will show you. So first, let's see the results. So compared to the passive device, so this side is a passive device, and this side is EMG controlled. And then you can see the posture. Because the passive device doesn't bend that much, so he has to really use the back and the intact side to compensate this task. And then you can see how beautiful on this side is the posture. This is a standard way for the lifting weight. And we know if you use too much back on lifting, it's going to cause a secondary injury. The other amazing thing is the synchronization and the modulation of a center of pressure in the anterior-posterior direction on the prosthesis side. So blue line shows the COP, center of pressure, of prosthetic side, and the gray line is the intact side. When he used the passive device, so the prosthetic side barely modulating. But when he started to using the EMG control after training, it's not only beautifully modulating, but also synchronized so well with the intact side. If you run the correlation coefficient, zero lag, basically see how well this two curve match. The value is much higher than using a passive device. Okay, and then also we want to see a training effect. So training from day one all the way to the end. And then we still focus on this cross-correlation of the COP bilaterally with zero lag, so just that value. As you can see, there are cross days, and then this value started to increase and somehow saturate on a certain value. So they start, and then also the biggest improvement is actually in the day one. So if you look at the day one cross multiple trial. So that means once they understand the consequence of activate this muscle became biomechanically have a function on that ankle, and then they would start to learn that really quick, just one day. Another amazing thing we saw is the synchronization of a bilateral EMG in the shank muscles. So in the day one, here is a day 5. So this is showing the bilateral TA EMG in the tibialis anterior. And the blue is the prosthetic side, so residual muscle. And then the curve, the gray curve is the intact side. So at the beginning, the two muscle bilaterally was not that synchronized well. But after the training, so these two muscles are well synchronized. Some of the peak is well aligned with each other. So this motivated me to think maybe, perhaps, the person restore somehow the neural pathway once the EMG, right? So once the residual muscle activity became meaningful again, and then restore the original biomechanic function. So of course, additional research is required because we only did a case study, but very exciting. So just a recap, we talk about the two types of neural control. One is a supervised that enable a terrain adaptation. I also talk about the direct EMG control that the potential has a lot of potential, but has to somehow has to coupled with appropriate training of the patients. And then we also see when people use the direct control, given them a sufficient amount of training, really help them to adapt their residual muscle activity in order to generate appropriate and more efficient direct EMG control of a prosthetic joint. Okay, so the future. I recently also see a lot of emerging of another research area is people trying to generating all kind of afferent neural interface. So the interface came back. So give a sensation of the foot, and sometimes it's a joint angle. So I'm very excited to close the loop because right? So when we have a neural control, and the person also not only understand their consequence of the action, but also they know how they contact with the environment. Would that really help the function further? That's an exciting research direction. I think it has a lot of promising. Look forward to read more from different group about their research. Okay, with that, I want to thank everyone for your attention, and I'm ready for your questions. Thanks.
All right, so let's welcome Helen joining us now live from North Carolina. Good morning, Helen.
Hello, how are you?
Good, thank you. Thank you very much for this very inspiring talk and also for sharing these exciting results. Now let's move to the question. So let me ask you the first one. So the changes in muscle activity that you reported at the end over the days are quite impressive. So I was just wondering what's your explanation for this? Is it just the subject that is learning to use and to somehow trust the prosthesis better?
So I personally think that this is really the restoration of the neural pathway. So think about the residual muscle no longer have a biomechanical function, then the person will not recruit those muscle appropriately. That's why you see some people could only activate one muscle at a time. This might also relate to the surgery as well. But if you give back the biomechanical function of this muscle, then you see there's the activity became more closer to what we observe in an able-bodied person. So I'm really excited because I haven't really conducted a more neurophysiology study on this, but I'm interested to see if this is because the way they can restore their original neural pathway for recruiting the muscle and then perform the task like what an able-bodied person could do.
And what was the feedback of the subject during this learning phase?
Oh, he's excited. He saw that this, a lot of tasks he would not. Well, he can do, for example, like the weight transfer that I show, he can, but he has to use a compensation. And then now he would be able to use that ankle again. And then just seeing, contracting the muscle would be allowed him to moving those the ankle that he lost for 3 years. It's a huge for him.
Fantastic, thank you very much. Let's turn to the audience and see if we have a few questions. Yes, we have. So, how robust does the EMG recording work? Is the recorded signal sensitive to leg stump loading? How is the repetition accuracy after donning and doffing of the device?
Oh, this is a great question. So, first of all, I wanted to emphasize, so actually our paper on that the case study is still in review. So we did a very careful design of the socket. So the socket feeding is really important to get a good EMG recording, that's for sure. And then the other one is because the direct EMG control, we are more using the, just a highly smooth envelope, so the magnitude. So therefore, So one aspect is the human would quickly adapt to it, and then two, it was not very, very noisy, compared to, let's say, pattern recognition that you need to capture very detailed EMG information like maybe wavelengths or zero crossing the frequency domain. So that's a difference in terms of when we say the reliability part. So I think it's dependent on what information you actually capture. And I am also very excited about the current technology for can embed the EMG recording directly in the muscle. So I think that's also a future direction. If that's available, potentially this control could be more reliable.
Absolutely. Let's move to the next question. So what's the percentage of subject in group 3 when you, in the study you showed, so not able to co-contract? And do you know how many of them significantly improve their co-contraction? to what does this relate? For example, is it linked to the type of injury or to time or to the surgery they had and so on?
Yes, so this is another great question. I wish I can answer you for sure. So in terms of a percentage, that in this group, there are 2 people out of 10, so 20% in our small sample, of course. And then we did not train them to expand further. So, if we conduct that, the research will be great, see if they can expand more. For people has a limited co-activation pattern, when we put them on the like inward pendulum, virtual inward pendulum control, they have they still improve the task performance, but they do not well shaping their muscle co-activation, like the strategy for using that muscle activation is not aligned with other subjects we recruited. Again, I recommend you read more, because in the paper we have a more report about it. And then address the last one, what is the reason? We don't know. We thought that maybe this is related to surgery, maybe the number of years, half amputation, but because the sample size is also relatively small, we can't for sure answer those questions. And then nobody really reports their surgical technique. That's another thing. So I also think in the field, I highly think it's important to know what type of surgery, and there's a new surgical technique is available. Maybe those surgical technique would help further.
Thank you, very important. Yeah, so we have another question. So how does it make you feel when you see a patient have success or improve?
That's everything. That's the thing that keeps me motivated to do this type of research. We are very, very excited every time we saw, our patients are excited about our technology, and then it does show a significant improve on a certain aspect. So absolutely, we are very excited.
Beautiful. So I guess it's a beautiful message to end this question session. I would like to thank you again very much, Helen, for joining us today. And of course, I wish you a nice rest of the day. Thank you.
Thank you for having me.
Okay. So the next short talk will also be on the topic of leg prosthesis, and it will be given by Joost Geroms. He's a postdoctoral researcher at the Vrije Universiteit Brussels in Belgium. His research revolves around active prosthetics and more generally mechatronics actuators, focusing on bio-inspired and energy-efficient design, as well as low and high-level control algorithm. He is also very familiar with the Cybathlon, as he was co-leading the VUB CyberLeg team that participated in the Cybathlon 2016 edition. Joost will share with us today his work on the development of the CyberLeg's X-Leg, lessons from active prosthetics research. Joost, the floor is yours.
Hello. Thank you very much for the introduction. Thank you all for attending this virtual presentation about the work of myself, some of my colleagues, over the past few years. The story starts a bit before the first Cybathlon, 2016, so about 5 years ago, at the end of the FP7-funded CyberLegs project, where we, from VUB, developed an active transfemoral prosthesis aimed at elderly dysvascular amputees, so often with comorbidities, weaknesses in the rest of their body. We try to enable them to remain an active part of society. To do this, the project combined our prosthesis with an exoskeleton that supports the rest of the body. It ended in 2015, after which we decided to participate in the Cybathlon with our research prototype. We learned quickly that it was not such an easy transition, as the requirements for our research device were very different from those of a device to participate in such a challenging live demo. Our device was quite robust, both mechanically and in terms of control, which we showed together with the CyberLex consortium in several research papers. But this was still a technology readiness level toward TRL4 device, not really ready for use outside the lab. We had to make significant changes to be able to achieve the required accuracy, for example, in high-level control and user safety. We had a lot of technical capabilities on board the prosthesis, but with this came very high complexity in terms of control. So this means that while we were able to have specific control strategies programmed for slope walking, stair climbing, forward walking, backward walking, we didn't have the ability to sense the user intention accurately and reliably enough for use during competitions such as the Cybathlon. Technically, this meant we had to replace the automatic high-level control, which used CyberLeg's wearable sensory apparatus that includes 7 IMUs and pressure-sensitive insoles, by a touchscreen user input, which you can see here on the wrist. We mounted it on the wrist of our pilot. Besides this, the controller we used was running on a normal Dell laptop, which our pilot also had to carry on his back, which is, of course, not very convenient. Addition of covers and such, which were less important for our research device, made the device a lot bigger and more cumbersome than it was before. After the Cybathlon, we had the opportunity to continue our work, together also with the CyberLex consortium, and also new partners, like, for example, Össur from Iceland. And we were able to do this because we were awarded the Horizon 2020 CyberLex Plus project. And the aim was exactly to take the technology we developed in the CyberLex project and take it further, increase TRL and make our device, the technology of our devices more market ready. The first prototype we made was an incremental upgrade of our existing prototype, more robust, more reliable, also able to be tested for a longer time with more subjects. And we made this based on the learnings we had from the Cybathlon participation. We included covers, for example, as much as possible in the redesign to make them acceptable in size. At this time, however, we did not have the resources yet to include redesign in terms of size and weight, or to reduce the size and weight. We organized an experiment with 8 subjects, which was including a short training session and then a number of tasks, everyday tasks, like stair climbing, timed up and go task, where the users had to start from a seated position, stand up, walk on a catwalk, go back and sit down again. More also sit-to-stand tests, and also a 2-minute dual task to investigate cognitive load while using the prosthesis. All of this compared to their own prosthesis. So one thing we were able to show is that all subjects, so they were all walking with mechanical or pneumatic knees of their own, we enabled all of them to perform stair climbing step over step, which they were not able to do with their own prosthesis. Also, the user group that we used for these tests, for this protocol, were not young, sporty subjects, but also elderly subjects. For all other tasks that we tested, though, the results were pretty inconclusive. Varying from neutral to slightly negative, but in general not showing any real big benefit for our device, which is unfortunately a trend we still see in general for powered prosthetics in the literature. We did allow, as we said, or as I said before, for step-over-step stair climbing. Scientists, however, generally like to see what percentage your performance increases with one device versus another. This is very hard to do in this case. This is basically another way of performing the task. These results are right now still under consideration for publication in Disability and Rehabilitation. So After several years of prosthetic investigation, we still face the problem that we cannot prove the efficacy of our device because we have the disadvantage of increased size and weight compared to commercial devices. So the focus for the next prototype we made was to try to address these problems of size and weight based on our past results. So one thing we did, the device we made in the final device we made, we called the CyberLex X-Leg to also get away a bit from the incremental names, alpha, beta, gamma prosthesis. I think it fits also more for a device that should be a bit closer to being market ready. So rather than developing an integrated knee-ankle prosthesis with the aim of, which we did with the aim of exploring synergies between the knee and the ankle joint, we decided to simplify, separate the ankle and the knee prosthesis. While energy input at the knee and ankle can be useful at both joints, a person with transfemoral amputation might have a larger benefit from a lighter, non-powered ankle in combination with the powered knee. Or at least that's a hypothesis that we have now. Besides this, we advanced the prosthesis in numerous technical aspects, solving many of the problems we encountered during our experiments or during Cybathlon. We increased, for example, the range of motion up to 120 degrees for the knee. We reduced the build height for both modules, so we can allow more people to test our device. But mainly, we reduced the weight by quite a bit. So we went to 3.8 kilos for 2 modules combined, compared to over 5 kilos for the previous iteration. Also, this weight includes everything required to power the combined knee-ankle prosthesis. So integrated LiPo battery, power and control electronics, able to perform high-level control, and also interface with the other modules developed in CyberLex++. So it's actually already more control power than we need to only power the prosthesis. Other modules, as I said before, could be the IMU's pressure-sensitive insoles. Also, I have to say, these electronics are not our own merit, but were developed at SSSA, Professor Nicola Vitiello's group. Finally, also aesthetically, I think we really managed to improve our device a lot, which can for sure help for user acceptance. And we hope that these advances will allow us to really investigate the advantages of our actuators and actuation methods. We were ready to start larger scale experiments at the beginning of the year, January, February, but that did not quite work out the way we had planned, unfortunately. We have performed a number of initial experiments, but past year has not been very kind to people doing trials involving people. So we are currently still working on that. Also, for that reason, the participation to the Cybathlon in the new format, unfortunately, was very difficult for us, given the small team we have to prepare for this event. We hope, however, to be able to present more results of our new devices soon. With that, I would like to thank you for your attention, and I will be happy to answer any question you have regarding my presentation. Thank you very much.
Okay, so let's welcome Joost, joining us live from Belgium. Hello, welcome.
Hello.
Thank you very much for your very nice talk as well. It was very nice to see the evolution of your research prototypes and also the impact that the Cybathlon had on that process. Maybe let me start with a quick technical question. So, what is the uniqueness in the mechanical designs of your CyberLeg concept? Can you tell us a little bit more about it?
So we actually developed several concepts already that we tested within the CyberLegs. So in the first prototypes, we really went, as I said, for the synergies between knee and the ankle. So if you look at a human walking, the knee is more a braking device or braking joint. So you dissipate energy in the knee where you walk, while the ankle is an energy-producing joint. So you need a lot of extra energy to be propelled forward. And so what we tried in the beginning is to exploit that synergy But of course, with that comes extra complexity and also limits the use of the prosthesis a bit to walking, because in other tasks, you have less of these synergies. And so I think this is good for research prototypes. But if you want to go more, if we, like we did later, then go towards more higher TRLs, we kind of abandoned these ideas a bit. We investigated them with our prototypes, but at later prototypes we went more looking at ways to control our device and things like that.
Mm-hmm. Yeah, I think I saw in one of the slides also the presence of a spring element, right? Was this correct? So
yes.
We saw a talk yesterday.
This is also still the case. Yeah, sorry, it's still the case in our last designs to exploit series and parallel elasticity as much as possible to reduce the required motor power for the several tasks.
Yeah, we saw yesterday, I think, in the exoskeleton section that this can also have an effect on dealing with, for example, uneven ground. So do you see the same benefit in your design for the leg prosthesis?
Yes, I think for sure. I think compared to having a direct drive or to have a solid control of your ankle joint, for example, is I think not desired in many cases. So I think having the complete there allows you to have a more natural behavior of your prosthesis without having to really control it into a certain mode.
Yeah, absolutely. So let me turn to the audience and see if we have any question. So one question for you. Thank you, Joost. Great work. Is it possible to control both joints of the X-leg with one controller? Or is it possible to investigate the energy efficiency in detail?
So it's for sure possible. And so as I said, we have one electronic, one battery still to control both joints, which is all included in the prosthesis. How well that works altogether, we still have to investigate. And so in the first instance, we went to looking at the knee separate in combination with the passive ankle and looking at the ankle separate, which is also possible and allows you to exclude the effect of one on the other. And so you can really investigate the ankle behavior by itself and the knee behavior by itself. But that is for sure possible. For the combination of both joints, we still have to go in more detail to see what benefits we can get exactly there.
Thank you for the answer. No more questions from the audience, so I'll ask another one myself. So I found it very interesting what you mentioned, that it was rather difficult to evaluate the benefits of the CyberLeg Plus in the assessment of the task that you use. Which also illustrates more the challenges of assistive technology evaluation, as we have also discussed already yesterday. But what was the feedback from the participants? Like, do you have such data? What did they report? Any advantage, like during interviews, for example?
Yes, we also included questionnaires, and also there was a bit mixed results. I think in general, the amputees were very positive about the fact that they could do the stair climbing, and that for them was a sensation some of them hadn't had for 20 or 30 years, how it feels like to take stairs normally. Mm-hmm. But in general, I think we need to look at a bit more things. I think also training is also something that comes back in literature a lot. We need to train more, but also it's not so easy to have subjects come in for months to do this extensive training. So yeah, I think most of them were positive about our device despite the high weight. So that for me is promising when we look at testing our new device.
Okay, so let's close the session here. Thank you very much for all your answers, and thank you as well for joining us today.
Thanks for having me. Goodbye.
Okay, so it is no time to close the leg prosthesis block. And before we move to our last short talk of the symposium, we would like to show you a short video to introduce the newly created Competence Center in Rehabilitation Engineering and Science at ETH Zurich. Enjoy!
Do you know that ETH Zurich launched a Competence Center for Rehabilitation Engineering and Science? Hi, my name is Oliver Stoller, and I'm the Executive Director of RESC. Please take a few minutes to learn more about our vision and mission. So welcome to RESC. Our mission is to make the environment and our society more inclusive in general. We foster a holistic rehabilitation approach towards a comprehensive management of physical impairments. So here's the background. Persons living with physical disabilities face numerous challenges and obstacles in their everyday life and can lose their autonomy. This affects their quality of life, prevents them from fully participating in and contributing to the society, and creates a socio-economic burden. Currently, persons with physical disabilities are seen and treated by medical staff for specific periods and are then lost track of without the clear management of further treatment and status. This means that the current approach to rehabilitation is highly fragmented in time and in space. Furthermore, acceptance for novel treatments and technologies is rather low. The high financial burdens associated with fragmented rehabilitation processes prevent an optimized long-term, independence-oriented treatment. The aim of RESC is to transition from the current focal, short-term, and fragmented system to a long-term solution offering personalized prevention programs, early as possible and continuous treatments, and assistance in the home and work environments. Our approach is an interdisciplinary network of experts. In collaboration with clinical partners, healthcare and disability organizations, industry and governmental institutes, we promote the development of need-driven and human-centered solutions to shape the future of rehabilitation. We establish a network, foster dialogue, and provide access for the science community, for partners in the industry and service provider sector, the public, and most importantly, for persons living with a disability. So very specifically, we foster interdisciplinary research and education to advance the field of rehabilitation, and we facilitate access to applied research and innovations for our partners. This will improve the quality of life for persons living with a disability and contribute to an inclusive society for all. Are you a person living with a disability, an industry or service provider, a researcher, or just interested in shaping the rehabilitation of tomorrow and make our society more inclusive? Please contact us for any kind of request. We are happy to connect and discuss. Please visit us on resc.ethz.ch for further information. We hope to talk to you soon.
Thank you very much, Oliver, for this introduction of the RESC and the offer to connect and exchange. We now come to the last talk of the day on a topic that is of general importance to the field, namely that of ethical design. It will be given by Dr. Marcello Jenka. Marcello is a senior researcher at the Health Ethics and Policy Lab at ETH Zurich. He's principal investigator in the project Digitalizing Elderly Care in Switzerland. His research focuses on responsible innovation for emerging technologies at the human-machine interface, technology assessment, ethically aligned design in health technology, and robot ethics. Marcello also is a member of the steering group on neurotechnology of the OECD, the Organization for Economic Cooperation and Development. Marcello, thank you for being here, and we look forward to your talk.
So before I start, I would like to thank Robert Wiener, Roger Gastert, Oliver Lambercy, and all the people who made it possible to have the Cybathlon and the Cybathlon Symposium this year, in spite of the difficulties, the great difficulties caused by the current ongoing COVID-19 pandemic. So my presentation tackles the topic of ethical design in rehabilitation engineering and health technology. And as such, it attempts to complement the excellent previous presentations from today with an ethical and social perspective on technology development and assessment. And this perspective is solicited by a broader conceptualization of care, well-being, and health to better encompass holistic understandings of health and illness in a manner that gives sufficient attention to societal understandings, principles, and structures underpinning health and well-being, as recently stated and promoted by the European Group on Ethics in Science and New Technologies. Now, a major approach to promote this holistic view of health and well-being into assistive technology is ethical design. And ethical design is basically a collaborative approach between engineers, ethicists, and other researchers, such as social scientists and so on, aimed at incorporating ethical considerations such as safety, well-being, autonomy, early on in the design and development of new technologies in order to make them ethical by design. And it involves the promotion of safety and well-being through adequate validation, the involvement of end users by user-centered design, and the consideration of ethical and social determinants of well-being, such as privacy, intrusiveness, autonomy, and so on. Now, it is important to highlight that rehabilitation and assistive robotic devices are inherently ethical classes of technological innovation, as they are purposively designed to empower people with disabilities and enhance their safety, well-being, and autonomy. However, ethical motivation may not always result automatically in the systematic incorporation of ethical consideration into technology design. So when talking about ethical design at the symposium 4 years ago, I was sharing with the audience how the engineering ethics community was actually going through a paradigm shift from reactive to proactive ethics. So from a mode of ethics as post-hoc evaluation of existing technology with no active participation of ethicists and social scientists in product design and development, little referral to user-centered designs and patient involvement, and it was basically a general view of ethics as evaluator of technology. And in contrast, the community was slowly moving towards a proactive ethics approach, which is based on the ex-ante incorporation of ethical considerations into technology design and assessment via user-centered approaches, and active collaboration between ethicists, clinicians, engineers, and other scientists, and was basically based on a general view of ethics as a facilitator, not evaluator of technology. However, in recent years, research has shown that involvement may not enough for achieving actual end user empowerment, because you need to involve end users in the right way. And similarly, collaboration per se may not be enough if the collaboration is not achieved in the right way. Now, just to give you a few examples, this is a study which showed that spinal cord injury participants involved in powered exoskeleton studies tend to perceive that outcome measures were mostly focused on assessing improved mobility while neglecting the quality of life of the target population. Similarly, a recent scoping review showed that while technical aspects of brain-computer interfaces such as usability or feasibility are being studied extensively, there is comparatively little in-depth research on self-image, self-experience of the BCI user. And sometimes these gaps in the implementation process may also affect the validity of measures, especially when it comes to measures for measuring qualitative well-being. For example, systematic review showed that more than 60% of usability studies on rehabilitation and assistive robot devices are reported to use non-valid or potentially biased measures. So what you can see here is that there are gaps that might emerge in the implementation process, or better said, in the translational process that goes from the designing labs to the actual clinical use of these technologies. So in order to overcome these gaps in the implementation process, I would argue that we have to embrace a second paradigm shift, which moves ethics from theory to practice, because ethical by design assistive tech cannot be achieved solely through a theoretical focus on design, but actually requires a practice-oriented focus and an active engagement with the implementation process. Now, my major tenet of this presentation is that this moving of ethical design and putting it into practice can be achieved in 3 steps. One step is improving the validity and reliability of assessment measures for usability studies and moving beyond custom-made measures and towards standardization. A second step is having an increased focus on the patient's experiential dimension, especially the quality of life, lived experience, satisfaction, and subjectivity of the user. And then finally, we need to align ethical principles, codes of conduct, standards, and regulation. And I will try to provide you with a few positive examples in each of these three domains that are being taken in the international community. So regarding improving the validity and reliability of measures and moving them beyond custom-made measures and towards standardization, a proposal is coming from the ASTM International, which is developing a guide to provide tools that help assess and ultimately improve the usefulness and usability of exoskeleton and exosuits, and is doing so primarily by achieving greater harmonization between assessment measures in this field. Another positive step in this direction has been taken earlier this year by the IEEE Standards Association, which released the Standards Roadmap and Newer Technologies for Brain-Machine Interfaces, which provides the first of its kind overview of existing and developing standards for brain-computer interfaces internationally. Regarding having an increased focus on the patient's experiential dimension, there are no international effort towards this harmonization to my knowledge, and this is much needed. However, some studies have shown a positive potential in developing qualitative measures for experiential dimension assessment. So, for example, this is a study conducted by the group of Roger Gassert and led by Jan Meyer, which showed that the user-centered design involving qualitative feedback via user experience questionnaire could improve the usability for exoskeleton end users. Another study showed that qualitative interview methods and grounded theory approaches can have a positive potential to assess user experiences among BCI users with disabilities. We have also developed an interview protocol involving interactive demos and narrative interviews, which is showing consistency across elderly users of several classes of assistive technologies as a viable tool to assess user experience and senses of safety and well-being. In terms of the third step, aligning ethical principles, codes of conduct, and regulation, I want to highlight the importance that in order to exert practical guidance, ethical principles should not remain just abstract moral desiderata, but they must be translated into actionable codes of conduct, standards, and ultimately regulation. A positive example in this direction is how the ethical principle of beneficence, which is one of the 4 principles of biomedical ethics, has been translated into a code of conduct by the RESNA, the Rehabilitation Engineering and Assistive Technology Society of North America, which states in its first tenet that the welfare of persons should be held paramount. And it has also been translated into actual regulation, such as in the UK CARE Act from 2014, which also puts emphasis on promotion of well-being. And it's important that this alignment of ethical principles, codes of conduct, and regulation can achieve what Alan Weinfeld and Gerard have called ethical governance. And that this is exactly what can be achieved by harmonizing actual regulation with ethical principles and standards. Another positive examples that I wanted to show is how the ethical principles of non-maleficence, which translates into the field of neurotechnology, especially brain-computer interfaces, into the notions of neurosafety and neurosecurity, has been translated into standards such as the ISO 13482, which sets safety requirements for personal care robots, and into actual robot safety legislation in jurisdictions such as the European Union and the United States. And then finally, I want to conclude by highlighting how this process of harmonizing ethics with standards and regulation is happening not only at the level of individual ethical principles, but also at the level of entire frameworks. And a positive example in this direction is the OECD recommendation on responsible innovation in neurotechnology, which sets the first international standards on the governance of brain-computer interfaces and other neurotechnologies. And as a member of the OECD steering group on neurotechnology, I had the privilege to contribute to the drafting of this document. And a lot of the preparatory work we did was precisely devoted to aligning this governance document with existing work on standardization, such as the previously mentioned efforts by IEEE standards, and also with the existing ethical frameworks, such as those developed within the International Neuroethics Society and several groups of researchers worldwide. So this is just to show how positive steps are being taken into the development of a more practice-oriented ethical approach to technology design and assessment. And with this, I would like to thank you for your attention.
We now welcome Marcello live with us here in the studio. Marcello, thanks so much for your talk and for being with us today.
Thank you, Roger.
And thank you also for reminding us that the work we do is inherently ethical.
Absolutely.
So you mentioned that we need to involve end users in the right way, and you also gave some perspectives on how that can be done. So where do you think we should start when we try to consider ethical implications more? I'm now talking especially from the point of view of engineers. Is it mostly the outcome measures we should focus on, or where can we make the biggest impact?
Yeah, that's a very good question, and it's not easy to say, well, this is there's a one-size-fits-all approach that can fix the problems. I would argue that since our goal as a community, extended community, is that of empowering end users, we should probably really start from the needs and wishes of end users, because there is nothing more ethical we can do than incorporating those end users and wishes into actual product design, because this can also create a sort of positive snowball effect. Once we have integrated accurately the wishes and needs of end users, we are in a much better position to empower them and improve their health outcomes. So I would say the focus on outcomes is more a consequence of the right focus on needs assessment and integration.
Thank you. A really related question is maybe, we're used in our field to doing trials with a large number of subjects, and if we present subjective feedback from individuals, we often get the comment, you need more participants in your study to say anything. So do you think as a field we need to evolve how we run these studies and what we accept as relevant steps forward, and in the sense of maybe publishing more single case studies also?
Yeah, so this is a very good question, and it's easy from the perspective of an ethicist to say we should involve end users more extensively. But when I refer to a practice-oriented approach to ethics, I'm also very aware and mindful that this kind of studies are time-consuming. For companies who are operate in the private market can also be more costly. So we have to be aware of these challenges, but I think we should really try to find the creative ways to overcome these challenges. And as you said, one of publishing more single case studies could be one approach. I would argue that also maybe expediting in certain circumstances the process that leads to ethics approval for involving more patients could facilitate the participation. And then I think public understanding is very, very important, because if we do the right work on raising awareness and providing good public understanding about the technologies we develop, and the Cybathlon is the perfect platform to do this, and it's actually actively doing this internationally, then we also build trust within and among end users. And if we build end users' trust, we are much better chances of involving them in the right way. So it's a sort of virtuous circle that we initiate.
Thank you. Let's see if we have a question from the audience. Hi, Marcello. Thanks for the talk. What is your take on the ethical conundrum that involving end users in the early development of unsafe robotic prototypes might be more and not less, might bear more and not less risks?
Yeah, I mean, this is a well-known conundrum, but this is based on this on the assumption that if we include end users, there are inherent risks associated with the inclusion per se. If we start from an assessment of end users' needs and wishes, we are also one step ahead towards minimizing risks, because we know much better where the end users come from and in which direction our research project can take. But this is something that we should definitely take into consideration, especially when we conduct research with vulnerable groups, such as people with neurological psychiatric condition, or senior citizens, or children. So this is a very important conundrum, which I don't think it's unsurmountable. but this is something important to take into consideration.
Thank you. Let's take another question from the audience. What could result if there were no ethical standards?
That's a sort of moral psychology question. What would people do if there were no standards at all? There is the optimistic answer to this, which is we would have a super effective self-regulation. So everyone will be absolutely able to self-regulate and develop products in the most ethically aligned way. And then there is the pessimistic answer, which is it would be just a hell out. I tend to be realistic, so probably neither optimistic nor pessimistic, or maybe more tending towards optimism, because I think that most people, a large majority, I would say, in the robotics community are well-intentioned and want to develop products that can have an impact in the world. Even more within the neurorehabilitation and assistive technology community, because as I mentioned, these technologies are inherently ethical and they are inherently designed to empower people and enhance their safety and well-being. So I would think that even without standards, most things would go the right way. But this is not enough. I guess as a community, we want to make sure that as many things as possible can go the right way. And that's where ethics can help, I think.
Wonderful. So I guess a good mix of optimism and regulations will be the way forward. Thank you so much, Marcello, for being with us, and thanks for your talk.
Thank you.
All right, with this, the Cybathlon Symposium 2020 is coming to an end. I would like to invite Olivier to join me here so that we can say a few concluding words together. Let's see if we can fit on the screen.
There we go. Right.
And maintain.
Quite nice to be next to you. Great, thanks, Roger. I think we had an amazing event, and I was extremely impressed with all what we've seen and heard on these 2 days. I will take home the message of Amit Goffer, our first keynote speaker, and it was also further highlighted in the testimonials regarding importance of including users and their needs in development and evaluation of assistive technology. I also was really impressed by the drive and the motivation of all the Cybathlon pilots who want to push the limits that are imposed by their disability. And you, Roger?
I was also touched by the testimonials of Mark and Maria and how tightly they are integrated in the teams and involved in the developments. I feel that we already saw more and stronger user involvement in our talks than at the first Cybathlon Symposium 4 years ago. And I am convinced that the Cybathlon and our discussions here will further support this positive evolution in the field. Most importantly, of course, I'm very happy that the virtual format worked so well and still allowed us to reach this level of interaction and quality of the talks and posters. Of course, all of this was only possible thanks to the incredible efforts of many people working in the background. From the initial thought of holding a physical symposium in Zurich to the implementation of this virtual event, which resulted in many unexpected challenges. Let's just say that we and everyone who worked with us went through a really steep learning curve over the last weeks.
So I guess that's the moment where we have to thank everyone, right?
I would say.
Okay, right. So many people worked hard with us in the last months. In particular, we would like to thank Anne, Roland, Stefan, Maya, Nadine, Miriam, Mohamed, Bruno, and Jean-Claude for the incredible support the past few weeks and months. A big thank you as well to the entire OnStage team, which helped us with many last-minute adjustments, and as you may see on the pictures, turn our lab down here into a professional TV studio and turn the two researchers that we are into some kinds of TV presenters.
Indeed, a big thank you to all of them. Additionally, I also want to thank the colleagues who helped us make this event highly accessible, namely the international sign language interpreters who signed the entire event live from the room just next to us, and also the closed captioning services. Finally, we'd like to extend a huge thank you to all our speakers and poster participants who showed tremendous flexibility and patience as we were figuring out how to run this virtual event. For this, we also had great support from all of our lab members, whom I'd also like to thank from the bottom of my heart. Finally, we'd like to thank our symposium partner, the Stavros Niarchos Foundation, again, for their continued support as we transited into this new format. This is just the beginning of the new Cybathlon era. We look forward to the Cybathlon competition in the new global format and already wish all the participating teams best of luck in the preparations and at the races. So thank you, everyone, and see you at the Cybathlon Global Edition in November.
There you go.